We're going to take a look at the direct comparison test, and in the first example, we're going to apply it to convergence, but then after that, we're going to apply it to divergence, and then we're going to apply it to, it's not going to work in this case. The series we're going to work with is this thing right there, and to do the direct comparison test, before you launch, you have to at least have a suspicion of convergence or divergence. So when I look at this series, I say, wow, it looks like that denominator is going to get pretty powerful compared to the numerator as we head out to infinity, making each individual term very tiny, making their addition to the sequence of partial sums very tiny, meaning the sequence of partial sums will eventually cease to grow any larger. That's convergence. So I suspect convergence. So I need to choose a comparison series that I know is convergent. So that's the first unusual step from this test. This is the series I'm working with, but out of thin air, I have chosen this series to be a comparison series. Now, when I choose a comparison series, I have to choose a series that I know matches what I suspect. And so I know this is a convergent series, so it matches what I suspect. I also have to choose a series that I feel comfortable working with, and 1 over n squared is a pretty simple convergent series. I know it's a convergent p-series. And I should also probably choose that comparison series so it's somehow or another related to this series. And although that's not mandatory, it's going to be helpful. So in this case, when I looked at that, I said, hey, as n is approaching infinity, that 1 ceases to really matter in the calculations. So it's really kind of an n-ish over n cubed, which if I reduce it is really a 1 over n squared. So 1 over n squared is a really good match for that for many different reasons. Choosing your comparison series, though, is going to take a little bit of practice, and it's a little bit of an art form. But as you've heard in many commercials, wait, there's more. Not only do you have to thoughtfully choose your comparison series like I had already gone over, but there's one other thing, and it's a very important thing. The following relationship is going to have to hold true between these two series. If I'm suspecting convergence, as n approaches infinity, or for all n, I need to have this relationship hold true. Each individual term in this one has to be greater than each individual term in that one. And I think the fine print in the math books say for all n, but if this holds true as n approaches infinity, but it isn't true for maybe n equals 1 and n equals 2 and n equals 3, I think this test is still going to hold true. But this relationship right here is super important. So we're going to take a closer look at that, and it's going to be the foundation of our logic. I've went ahead down below and I've taken my comparison series and written out the individual terms up to n equals 5, and the same thing with my actual series. And you'll notice for every single one of these, and it takes a little bit of arithmetic, but for every single one of these, this value is slightly smaller than this value. And you can see that trend is going to hold true as we head out to infinity. So I've met this condition, this very, very important condition. This is where the deep thinking comes in. So let's take a look at that logic. We know that this comparison series is convergent. So if I think about it, that means if I would add up all the terms, all of these terms, it's going to add up to a specific number. It doesn't head to infinity, it ends up being a number. That number might be 17, might be 11, who the heck knows? Euler knows. Now, we're going to add to that. If each individual term of the real series is smaller than that of the comparison series, then the sum of this series has to be smaller than the sum of this series. Well, if the sum of this series is a number, and the sum of this series is going to be smaller than that, then the sum of this series has to be a number. And if the sum of this series has to be a number, that means that series is convergent because that's what it means to be convergent. So that's an awkward set of logic to put into words. I tried to put it into words here, but you may want to rewind and replay that logic again. In the end, I say, hey, this thing is convergent, and it's from the direct comparison test. It's really some nifty logic. Basically, we're using the comparison series to bully the real series into submission. In this case, it's into submission of convergence. The next example is going to be of divergence. Same idea, same logic, but there's going to be a few twists. So it's the direct comparison test, but now we're going to apply it to divergence. Here's a simple, relatively simple series, and I'm choosing relatively simple series right now so that we can get used to the logic. Take a look at this, and I have to have a suspicion. I suspect divergence, and this seems pretty darn related to this, and this is a famous divergent harmonic series, so this would be an excellent comparison series. But it's only an excellent comparison series if this relationship holds true. And as you might have picked up from the previous example, this relationship is the bedrock of the logic that's going to lead to our conclusion. So in this case, I need every individual term of the real series to be greater than the individual terms of the comparison series for all n, or at least for as n approaches infinity. Here's my check of that condition, and you'll see that it holds true as n approaches infinity, and it will stay holding true the whole way through. Just a small side note, I started this series at n equals 2 because n equals 1 would blow up the denominator, giving us an undefined. So every once in a while, don't let that slip by you. So we've suspected divergence, we've thoughtfully chosen a comparison series, we made sure that this holds true, and now this has to be the bedrock of the logic. So here's the logic. I know 1 over n is divergent, so if I were to add up all of these terms, they would add up to infinity. Well, if all of these terms are going to add up to infinity, and every single one of these is slightly greater than its related term, then all of these are going to have to add up to infinity and a little bit more than infinity. So I'm going to put that into words here. Hold on. So I attempted to put that logic into words again, but just remember this. If these are adding up to infinity, and I know these are greater terms, then these have to add up to infinity and a little bit more. If the sum of all these terms is infinity and a little bit more, then this thing better be divergent, and that's what we can conclude. Now I realize one of the stumbling blocks it looks like is that you have to memorize a relationship like this for divergence and a similar but different relationship like this for convergence. But if you're understanding the logic that's going on here, then that logic is going to dictate to you that a certain relationship has to exist when you choose your comparison series. So I'm trying to say it's not as much memorization of a fact as you think, but it's the application of an idea that helps you know that your memory is correct. I have no idea if that last statement made sense to you. If I had to restate it, I would say, it's going to be okay. Your logic is going to guide your memory. Like all of the tests we work with, you should understand that you could easily get no conclusion, either because this isn't going to be a good test or slight user error on your part. So I've given you an example. I've changed, this is a new series. We used to be working with 1 over n minus 1. Now we're with n plus 1. So I look at that, and I may or may not know if it's convergent or divergent, but I have to have a suspicion. If I suspect divergence, and I use this as a comparison series, then my condition is not met where this series is always a little bit greater than this series for each term. So either that means I shouldn't suspect divergence, or better yet, I need to come up with a better comparison series. But that might not even be possible in this case. If I suspected convergence and I wanted to use that as a comparison series, this condition is not met, which means maybe I shouldn't suspect convergence, or maybe I should come up with a better comparison series. So that's a little bit of a bummer because you don't necessarily know. You get to carve your own way, and for one problem, some person might use a comparison series that's different than another person, and they both can come up with a valid conclusion. So when you run into a problem, remember it could be that you're not picking a good series, or it could be that you're really just not going to come to a conclusion with the direct comparison test, and you would go on to a different test. In this case, we would say, okay, well, that's not happening. I should have already checked to see if it's a famous family, and if it's not a famous family, then I have to rely on another one of these. This is always a good one to do right off the bat before you do anything else, because a lot of times you can conclude divergence from this test and you don't have to bother doing anything else. All right, that has been the direct comparison test. It's a little bit weird in the beginning, but once you get it, you come to love the beauty of the logic.